let's expand upon the previous videos and let's talk a little bit about work and energy again. So let's talk about the work and energy theorem. The work and energy theorem says that when work is done, net work, let me be very specific, when net work is done on an object or a system, then there's going to be a change in that object or system's kinetic energy. All right, so I'm going to use the symbol T for kinetic energy. And so I've got kinetic energy at some point 1, and then I do work on that particle. Could be a system, but let's just stick with particles for now. Then I'm going to end up with some kinetic energy later on. Now, if the work is positive, the kinetic energy will increase. We'll start off with a lower kinetic energy, T1. T2 will be a larger kinetic energy. If the net work is negative, then the kinetic energy will go down. So T1 will be larger than T2 in that scenario. Okay, so T1, the kinetic energy at point 1, T2, the kinetic energy at point 2. And we'll get to the equation for kinetic energy in just a second. U then is the net work. Now, super important, right? The net work. It's not the work done by any specific force. It's the work done by all of the forces. And we might have to break that down into work done by force 1, force 2, force 3, etc. Okay, so let's take a look at an easy example. So I've got a box here with some mass m. Don't care what m is, but it's going to have some value. And it might have a velocity at this point right here, and it's sliding down the incline. So let's assume that it's moving down the incline here, and it's got some velocity v1. And then I'm interested in what's going on down here. It's going to have some velocity v2 there. Is that more than v1? I don't know. We'll have to work everything out as far as the numbers go in order to do that. There are 3 forces acting on the block as it slides down the incline. First, there's gravity. That's acting on the block, right? So that's going straight down. Then there's the normal force. That's going to be perpendicular, hence normal to the surface. And then a frictional force, and that's going to be dragging back. If the block is moving down, the frictional force is backward. Real quick thing here, frictional force is always opposed to motion. So it could be the acceleration is up, but the motion, the velocity is down. I don't care what the direction of the acceleration is for friction. I care what the direction of the velocity is. So if it's sliding down, and I just said it opposes the motion, I'm going to retract that. It opposes the sliding. In this case, the sliding and the motion are the same. In the case of an automobile that's going down the road, it might be traveling to the right. The frictional force is actually to the right in the same direction as the motion, because the frictional force is acting on the tire, right? So the tire is trying to rotate, take away the friction, and the tire spins, which means the bottom of the tire slides left on the road. It slides left, the frictional force is right. Okay, a little off tangent, but just wanted to clarify there. In this case, the frictional force is up the incline because the object is sliding down the incline. All right, so if I want to figure out, hey, what's going to be the kinetic energy at the bottom or the velocity at the bottom, then we can use the work and energy theorem right here. So first off, let me get rid of this for a second. I need to understand that the kinetic energy, by definition, kinetic energy is 1/2 mass times the velocity of 1 squared, because this is the kinetic energy at 1. So kinetic energy is 1/2 mv squared. So at position 1, it's going to be 1/2 the mass of the object, whatever that mass is, times its velocity squared. Now, kind of important, so this is really speed. I don't care what the velocity is. The direction is of no consequence with kinetic energy. I might write this as 1/2 mass velocity 1 dotted with velocity 1. And when I dot this with itself, I get a scalar. So this is speed squared, right? So a little careful about that one. Over here on the right-hand side, I'm going to have 1/2 m v2 squared, right? But what about the work here, the U? What's the work being done? Well, we've got to be careful. It's net work. I have 3 forces. All 3 of these could be doing work. Okay, so I'm going to add in here the net work. I'm just going to put that big parentheses there and I'll work down here. So let's do the easy one first, the normal force. Right, so the work done by the normal force, that's going to equal Fn dotted with the displacement, which is F delta R. Okay, so Fn points in this direction. Delta R points exactly at 90 degrees, and so delta R is perpendicular to Fn, Therefore, and let's put a vector sign there, this is equal to 0. Because Fn is perpendicular to delta R. So that's equal to 0. Done. All right. Frictional force. Let's do that one next. So the work done by the frictional force, that's going to equal the vector frictional force dotted with delta R. But what do you notice? You notice the frictional force is up the incline. Delta R is down the incline, so they're anti-parallel. So the angle in between them is 180 degrees, and therefore this is equal to minus the frictional force times the displacement. I've taken the vector signs off of there. Frictional force times displacement. It's going to be negative though, because the frictional force is in the opposite direction as delta R. And then finally, the work done by gravity. So that's going to be mg, which points down, dotted with the displacement. And so in order to figure this out, let's see, so this is theta. Let's bring this down here. So this is some angle alpha, but theta plus alpha are 90 degrees. So the angle between mg and delta R is alpha. So this is going to be mg, no vector sign anymore, delta R, and then the cosine of alpha, right? The cosine of alpha. But I want this in terms of theta, and so that's going to equal mg delta R sine of theta, because alpha and theta are complementary. In other words, they're the opposite sides, opposite angles of this 90-degree triangle. The cosine of alpha is equal to the sine of theta. And so the net work done then will be minus F delta R plus mg delta R sine theta. So I could say then that U net is going to equal mg sine theta minus F times delta R. And that would be the net work that goes up into this parentheses. And so whatever our numerical values are, we put all that together and we can figure out, depending on what we know and what we don't know, the kinetic energy or the velocity at the bottom. Okay? Real quick, let's take a look at units. I've got force times displacement. Okay, so my units are newtons times meters. That's for the work done. Newtons times meters. I've got 1/2 mv squared, so that's going to be kilograms. Meters per second quantity squared. But that's kilograms meters squared per second squared. Okay, getting a little crowded here. But let me just pop it over here. So I've got kilograms meters squared per second squared, but that's kilograms meters per second squared times meters. I just separated out the meters, right? The kilogram meters per second squared, that's newtons. So this is Newton meters. So the work done, the net work done is Newton meters. The kinetic energy has units of Newton meters, or kilogram meters squared per second squared, and we call those joules, named after a famous physicist, or just capital J for the symbol. And so those are the units we have in the metric system for work or for kinetic energy. In the English system, we generally use foot-pounds, right? Force times displacement. So pound times feet or foot-pounds. All right, if you have any questions, be sure to leave them in the comments below.